Hey there everyone, Mr. Dickin here. In this video we are going to be talking about the last of our function operations, and that is finding inverses. So far we've done adding, subtracting, multiplying, dividing. We've recently covered composition, and now we have inverses. Now, before we jump into specific examples, I just kind of want to give you the preview. The whole concept of an inverse is when you have an x and a y value, right? The coordinates x comma y, or even the x and y from an equation, and all they're doing is just switching. So they are inverting their roles. All right, so that's all we're going to be doing. If you can just kind of keep that in the back of your mind, you should be totally fine with this lesson. So, everyone's favorite, vocab. First off, a function, and we've already covered this. A function is a relation in which for every x, there we go. For every x, there's only one y. Right? So we had the vertical line test, making sure that no x is repeated. A one-to-one function is kind of the next level. So that's saying for every x, there's only one y, aka the function definition. But then it goes backwards. For every y, there's only one x. So that means the x's can't repeat, nor can the y's. Now with that, it introduces a new test, right? We already knew about the vertical line test, but now we're going to have a horizontal line test. And that horizontal line test ties in with the whole concept of for every y value, there can only be one x value. Now we care about the horizontal line test because that will tell us if the inverse is a function or not. We already know how to determine if a graph is a function or a table is a function. And now we have a way to determine if a graph has an inverse that is a function. All right, last bit of vocab here. This is more of a notation thing than anything. The way we represent inverse functions is right here with f, and it looks like an exponent of -1. This is read as the inverse of f of x. So this is the inverse function of f of x, right? You're not raising it to a specific power. That's just strictly notation, all right? All right, so first let's figure out if graphs are one-to-one functions or not. If they are one-to-one functions, then they will have an inverse function. If it's not one-to-one, they'll still have an inverse. However, that inverse will not be a function. All right, so first one, is it a function? I use the vertical line test. Yeah, it passes. So this is a function. Is it one-to-one, meaning does it pass the horizontal? No, because I'm seeing intersections here and here. It intersects at more than one spot, so it fails the horizontal line test. Therefore, it is not a one-to-one function. So its inverse would not be a function. All right, let's try a cubic over here to the third power, cubed, cubic. Oh boy. It passes the vertical line test. All good there. And it passes the horizontal line test. So that means this is one-to-one. So its inverse would be a function. All right, some more examples here. I'm going to go ahead and do the vertical line test just for all of them to get that done and out of the way. And it looks like they're all passing the vertical line test, so they are all in fact functions. Now let's try the horizontal line test. First one passes, so that would be a yes, it is one-to-one. This one would be a no, and that's kind of the upside down version of the one we just saw over on the previous slide. Next one, it looks like it fails because it actually intersects here, here, and here. And then the last one, horizontal test, yeah, it would pass. So as far as one-to-one goes, we have a yes, a no, and a yes. All right. Well, now let's get into how do we find the equations for these. And I'm going to harken back to the very first thing I told you. All we're doing is switching x and y, okay? So how we find an inverse function is we're going to take our function notation, And instead of writing f of x, we're going to use y, just because that tends to be easier for everybody. We are going to switch x and y, which means we are going to be inverting. So right here, this is the inverse step. Step 3 says solve for y, so basically get the new y by itself. So you're just getting y equals. And then we have our notation piece, which is going to be f with an exponent of -1 or superscript of x. All right, so these ones are pretty straightforward. First one, I'm going to think of this as y equals 2x minus 1. Then I'm going to go ahead and switch the x and y, so x equals 2y minus 1. And now my goal is just get y by itself. So I'm going to have to add 1 to the other side and then divide everything by 2. So I'm going to add 1 to the other side, x plus 1, and then divide everything by 2, and that equals y. So my inverse function is going to be x plus 1 all over 2. So the inverse function value evaluated at an x value of 5 would just be 5 plus 1 all over 2. Well, 5 plus 1 is 6. Divide that by 2. We're going to get 3. All right, same thing. Second one. Switch x and y. So x equals 1/3 y plus 7. Let's get that plus 7 to the other side. So x minus 7 equals 1/3 y. Now here's where some folks might get in trouble, because they'll see this 1/3 here and they'll get confused, right? Do I divide both sides by 1/3? I'm dividing by a fraction. What does that even look like? Well, if you think way, way, way back to when you first learned the properties of fractions, if I wanted to divide by 1/3, that's really the same as multiplying by the reciprocal, of 3 over 1. Because when I do that, the 3's will knock each other out. Well, I guess 1's by default are already knocked out. But by multiplying by a reciprocal, I'm just left with 1. So that's going to be 1y over on the right-hand side. Now, whatever I do to one side of the equation, I have to do to the other. We have to maintain a balance. So I'm going to multiply by 3 over 1 over on this side. Basically, we're just multiplying by 3. So if I distribute that in, I'd get 3x minus 21. So my inverse function is going to be 3x minus 21. And if I evaluated that at 2, that would be 3 times 2 minus 21. So 3 times 2, let's see, that's 6. Minus 21 would be negative 15. Neat. All right. Well, now let's talk about the whole graphing portion of this. Remember way, way back to the beginning of this video when I said the whole concept of inverses is just switching x and y. Well, that's really all you got to do when it comes time to graph. So when you're graphing an inverse, if you know coordinates on the original graph, to find the coordinates on the inverse, you just flip-flop them. That is it. It is literally that simple. Now, when you graph both of these at the same time, you'll know right away if you did it correctly, because they should create a mirror image over what's called the identity line, so the line y equals 1x. So if I were to kind of imagine that I folded this graph kind of diagonally onto itself, I should have mirror images created. That's all that that's saying. All right, so let's see an example here. I want to graph f and the inverse on the same coordinate plane. All right, so my function is going to be 2x minus 3, and judging by the table, I just need 3 values. I'm going to go simple here, and easy numbers for me to use are just going to be 0, 1, and 2. If I don't have to think hard, I'm not going to. So 0, 1, and 2. All right, so if I plugged in 0, 2 times 0 minus 3 is going to be negative 3. Over here, 2 times 1 minus 3 is going to be negative 1. 2 times 2 is 4, minus 3 is going to be positive 1. So when it comes time to graph, I have 0, negative 3, right here. I've got 1, negative 1, and I've got 2, comma 1. Now, yes, we could have also graphed that using what we know about slope-intercept form. The y-intercept is negative 3. Yep, got it. The slope is 2, so up 2 over 1. Yeah, got it. All right, so now the inverse, if I wanted to graph that, is just going to take all of these values in the initial table and switch them. So the first point set of 0, negative 3 is going to be negative 3, comma 0, and then negative 1, comma 1, and then 1, comma 2. So all we did is just flip-flop the x and y's. So when we graph, I have negative 3, comma 0, negative 1, comma 1, and then 1, comma 2. Now when I graph these, if I did it correctly, and I think I did, they should create mirror images over that provided dotted line. So there's my original function there in blue. And then if we graph the next one in red, there we go. So it looks like, yeah, they'd create mirror images of one another. Not too terribly difficult. All right, let's do one more. We'll go ahead and skip this last one. I feel like this last one is the simplest out of all of the three. So if you understood 1 and 2, you should be golden on that last one. However, you will still have the PDFs of the completed notes available to you. So if you want to see the work, that'll be available to you. All right. So we have 2/3 x plus 1. Now I could graph this, and this is going to be totally legal if I want to do this, of using the y-intercept and then my slope, which is up 2 over 3. All right, so if you wanted to do it that method, you'd have a y-intercept at 1, and then you'd go up 2 over 3, up 2 over 3, and you can repeat that process however many times you feel like until you've got the amount of points that you want. All right? Now, if we wanted to fill this in with a table, right, over here, here's going to be my suggestion. Let's not use 0, 1, and 2 for this next one because we don't have a clean coefficient. We have a denominator of 3. So that means the numbers I plug in for x, I want it to be something that can be easily divided by 3. So multiples of 3. I can plug in 0, 3, 6, 9, 12, whatever. But I'm not going to want to plug in like a 2 or a 5. Because if I try dividing that by 3, we'll get a weird fraction. Graphing fractions is a total pain. All right, so let's see. 0 is going to be easy, right? Because 0 times anything is just 0. Add 1 is going to be 1. Next up, I'll plug in 3, then I'll do 6. If I plugged in 3 for x, 2 times 3 is 6. Divided by 3 is going to be 2. Basically, the 3 is just canceled, right? So 2 plus 1, that's going to be 3. So I just got a value, 3, comma 3. If I plugged in 6, 2 times 6 is 12. Divide that by 3, I get 4. Add 1, we're at 5. So when it comes time to graph, we already had the 0, 1, we already had the 3, 3, we already had the 6, 5. So no surprise there. All right, so now let's get our inverse points. All I'm doing is just switching x and y, so that'd be 1, 0. This stays 3, 3, and this would be 5, 6. So on our graph, we have 1, comma 0, 3, comma 3, and then 5, comma 6. And I'm already kind of being able to tell that if I were to graph these, that we would get our inverse functions. Because they're creating that mirror image over the identity line. So that's it for graphing. Actually, before I cut this video, just for fun and sunshine, if we pretend, so pretend with me, if we pretend that it didn't want us to actually graph this, it just wanted the inverse of x, or sorry, of f of x. If we wanted to calculate that, I'd start off by switching x and y. So x equals 2/3 y plus 1. We'd move 1 to the other side. And then right here, to get rid of that 2/3, kind of what we talked about on a previous example, is we'd have to multiply both sides by its reciprocal, which would be 3/2. So over here on the right side, the 2's cancel, the 3's cancel, we're just left with y. That's what we want. Over here on the right side, we'd be able to distribute that in. So we would have 3/2 x minus 3/2, or if you wanted to use 1.5s here, you could, and that would be our inverse function. Whoops, cut the box a little too short. So if you would rather graph it from a function rule, you could. That's just kind of the method we'd have to go about for doing it. And you'll notice here on the graph, our slope is going up 3/2. And if I were to ballpark that y-intercept, it does look like it would be a negative 1.5 or negative 3/2. All right, that's it for this video. We are done. D-U-N, done. You guys know the drill. Do the problem set online that's provided for you. Let me know if you have any questions. And as always, folks, good luck, have fun, be safe, roll tide.